Okay, so then let's start with statistical methods. So the aim for today is essentially that we go over some introductory aspects before we delve into really content in terms of mathematical stuff, as you would refer to it. So the idea is that first I will discuss. I realized I should work on my that I don't spit on my device. I should work on that. I just realized. So the idea is that we first go over some basic terms that give you some background knowledge of what we are doing here before we really delve into that's Slack. I already find Slack annoying after 1 minute. I think I have to turn it off, but I saw there was a Slack discussion. Slack is great. I have to turn it off. Let's see whether I manage to do that now. So now without Slack. Good. So yeah, let's just get started and so that you know what I'll be talking about. So this first introductory session is more really to introduce some terms that will come up again and some fairly fundamental things. So first I want to talk about data analysis in general, and then basically talk a lot in terms of conceptual issues about models. What they are and so on, and from a more conceptual view, and then maybe in this hour or the hour afterwards give a first introduction to the general linear model before we then take a detour to some important mathematical fundamentals that you need to know. Okay, so data analysis. Maybe let's do that interactive. So what is data analysis? Can somebody tell me, if you think about in general, what is data analysis? What does that entail? Somebody. Caroline, what is data analysis for you?
Well, once data is collected, we need to organize it somehow, and then we want to extract some kind of knowledge from it. So we want to get the meaning of the data, and then we want to plot it. So it's about extracting information and summarizing.
Yep. I think this were actually already the 2 points or 2 key things that I want to stress. So you said extracting information and summarizing, and this is actually these are the things that I also want to tell you now. So I start with the thing that so data analysis is data reduction. So let's just put that here because we can now. I used to write it on the board. So data analysis is always data reduction. So you can see in the script there's this figure where there are a lot of colorful points in a square. Because this device is new to me, I don't know how to easily make colorful things at this point. I mean, I know that I can change the color, but I don't know how to do something like the figure there. Anyway, so a very important aspect of data analysis is that you start out with a lot of data points, and I guess you're all familiar with that, for example, if you're in psychology and you recorded some behavioral data, then you had a number of trials where you, for example, recorded reaction times, or you had a number of participants and you recorded some questionnaire. Then for each participant you have answers to a questionnaire, and then you have many participants. In the end, what you want to report in a scientific report, like a research paper, you usually don't want to just give the raw data to people you want to communicate with about your research project. But you will summarize the data somehow, and this is kind of so you want to summarize the data, like Caro said, and so you project many data points onto fewer data points. And that could, for example, be a mean of some data, a t-value. If you think about brain imaging, this could be that you have all these time points and bold values that we recorded from each voxel for all the participants. And in the end, you show a map where some brain region lights up. So this is also quantitative data, of course. So you summarize data. And that's especially in the age that we now live in, where data sets are quite easily get quite large. It's of course an important feature. Good, so that's relatively clear. This happens all the time when you analyze data, and is kind of a byproduct maybe of what also happens, and what is actually in my world, kind of the I don't know, is it more fundamental? It's kind of the thing that we do to extract information. So while we extract information, we're reducing the data, but one important thing that we always do is that we use a specific tool, a specific way to analyze the data, to interpret the data, which is known as a model. So the point that the whole course will make, and that is basically very at the heart of my personal activity in science, is that data analysis is model-based. And I want to explain that a little bit, what I mean by that. So there are, I guess, has anyone heard of a model-free data analysis technique? So has anyone, yeah? Yeah, exactly. So there are people that, so clustering was mentioned, and I think a lot of people also call, for example, PCA or ICA, model-free data analysis techniques. So there is this notion of data analysis techniques being model-free, which exists in the world, and people talk about that. I wouldn't agree. So I basically, one can write every model-free data analysis technique as a model-based technique by spelling out what's actually happening. So I know that it exists, and I'm aware that certain certain data analysis techniques are called model-free, but I wouldn't call them model-free. Just to get that out of the way. So from what we are doing here, data analysis is always model-based, and we will also in the summer term talk about so-called model-free data analysis techniques like PCA and ICA, and I will show you exactly what the model behind them is. One thing about model-free data analysis techniques is that the models are usually relatively let's say general, or maybe a little bit boring from my perspective. So what do I mean by data analysis is model-based? So essentially, I don't mean anything else as that data analysis is essentially the same thing as the scientific method. And this is kind of the conceptual view of what I'm trying to tell you in this course. And before we talk a very specific model, that but also something that really helps you to get into this whole model-based data analysis, I want to introduce you to this scientific method slash model-based analysis. And for this, there is this figure in the script, which I will now reproduce here and explain what I mean. So one thing that which some people already sometimes disagree with, but I'm fairly certain that I'm right, is that reality and the scientific method, model-based analysis, are two different things. So outside of science, there is something that you can call reality, And then reality can, in science, yield to something that would be called a measurement or data. Yeah. So this is this thinking about science or the scientific method. So this big rectangle here should be the scientific method. This thinking about the whole approach of science is, of course, somehow modeled on what we also do in cognitive neuroscience, so that you have basically the brain and you have the outside world, and the brain can, by its senses, collect some data. And data would be, for example, like the activity profile on the retina. But this is already part of the inference agent of the scientific method. So because, of course, it depends a lot of how data looks depending on what you acquire, right? So if you put electrodes onto the brain to acquire data, you get completely different data than if you put a participant in an fMRI scanner. So the data that you get is not something that is in this conceptualization, something that exists out there in the world, but it's something that is determined by the scientific method, the scientific process. And now, what we do in model-based analysis, or what we also call, because the course is called that, statistical methods, is that we somehow want to, like you said, we want to ascribe meaning to that data. We want to find sense in that data, extract, if you want, information from that data. But really, we want to. So I always think about it that you want to give meaning to data, and the data we are talking about here actually could also be of qualitative nature. So, for example, interviews, and then so verbal interviews, and then you can sit down and then try to extract meaning. What our course will be concerned with is quantitative data. So data really means large sets of numbers that are stored somehow digitally. Could also be of qualitative form. I think the scientific method applies to both cases, but here we are dealing with the quantitative form. So to now extract meaning and ascribe meaning to data, what we will cover in the course for the GLM, and then later for other methods also. Basically, it's a three-step procedure. So the first thing would be model formulation. So that is the process where we essentially take what we already think might be of interest in the data. We have an intuitive idea why we are doing the whole thing, right? So if you, for example, record fMRI data or EEG data, you have somehow the idea that something that happened or outside of the participant, or maybe even inside the participant, if you're talking about resting state, that somehow you can see that in these numbers that you get from the EEG device or from the fMRI device. And this very broad intuition is something that you then, if you analyze quantitative data, can put into some mathematical form and formalize. So maybe to make clear in terms of the GLM, because this is kind of the introductory part. In terms of the GLM, what I mean by this is that, first of all, I want a different color and it's not working. Now nothing works anymore. No, I think I have to press there. Why is it not working anymore? Just wanted to do something crazy, change the color, and now it's not working anymore. Pen. Pen is back. Color. Oh, do I have to go back? Aha. So press the different color and then go back to pen. Okay, so model formulation. In terms of the GLM, we will talk at length about this little equation here, which you're not supposed to understand at all right now, because we haven't talked about any of these things that are involved. But this is actually what, in terms of the GLM, model formulation is about. And if we then later talk about different analysis techniques, or you study analysis techniques yourself, you should always ask yourself, what is the model formulation aspect? Yeah. So that's the first thing that we discuss at length in terms of the GLM, so that you really get a feeling about what I mean by this rather abstract term, model formulation. Good. So the next thing is maybe one thing to stress about model formulation is also that this is something that is happening irrespective of reality and irrespective of data. Yeah, this is kind of a cognitive process that you on your own, or maybe with in joint work with other people, do to formulate something that will allow you to extract meaning from data. You can also, I mean, in more general terms, you can also call this theory formulation. Yeah, so I call it model formulation here all the time because it's we talk about the general linear model and not the general linear theory. But it's the same thing as creating a scientific theory, only in quantitative and formal, in a formalized sense. So the next thing that is very important then is that somehow, because we want to do science, we don't want to be computational neuroscientists who formulate models all the time and then they play around with them. We want to do science, so we want to estimate we want to estimate certain parameters. How do I call it here? Yeah, model estimation. We want to somehow bring our model in alignment, or at least related to the data. Yeah. So we don't want to only formulate models and play around with them, but usually models have three parameters that are basically things in a model, entities or quantities in a model that allow the data that are influenced by the data, and then we can interpret these parameters in some sense. And actually, this is maybe something that was, when you did your undergraduate statistics, was not discussed that much. Because I think a lot of the focus, especially in psychology, is on model evaluation, but we will discuss that at quite some length. So model estimation in our case is the formation of parameter estimates. For example, in terms of the GLM, it has a parameter called beta. We will talk at length about where this equation that I just wrote down here is coming from. There's another parameter of the GLM, which is a variance parameter, and we will talk about this estimation. We will talk in this context about maximum likelihood. So this then is the model estimation part. But model estimation can, of course, only happen once you have formulated a model. But it's very crucial, in my opinion, in the scientific method, because model estimation is really where this going together of theory and data in science really happens. And model estimation, I will also sometimes use the term inference for that, because things are not that clearly defined. But just that you are forewarned that I might use also sometimes different terms for that. Good, that's model evaluation. And then finally, the last thing is that, of course, now we have somehow let the data influence our model. We want to, it's actually not quite the last thing. The penultimate thing is model evaluation. So we have now some parameters estimated, and maybe also the probability of the data under the model estimated. And then we want to figure out what we can do with that. And this is something that you seen and heard about quite a lot in undergrad statistics, namely evaluating t or p-values. Yeah, so who has never heard about a t or p-value? No, the other way around. Who has heard about t and p-values? So that's most of you. So that's the model evaluation step, where you then kind of draw some conclusions and make some sense of what you have learned. And then finally, of course, to close the scientific circle, is that you use this information about what you have learned about your model or your theory to update your model formulation. Yeah, so that you now know that something is happening, and then you can change your model formulation and then see whether this actually makes your explanation of the data, which is part of reality, better. Okay, so this is essentially how I conceive data analysis. So one thing is that is data reduction, which is useful because our the raw data that we can acquire gets ever and ever larger. The other thing is that, of course, data analysis should ascribe meaning to data, and this is done in a model-based fashion. And as the example to get you into this thinking of a model-based data analysis, of course, we will deal with the general linear model to exemplify these three steps of model formulation, model estimation, and model evaluation, so that you've seen it once, like how this works for a specific model class. And then because there are many different data analytical procedures these days, you can use this kind of as a framework to think about different data analytical methods and learn about them. Good. So this is kind of the model-based approach to, or the model-based foundation, model-based framework for data analysis. Do you have questions about the things that I have currently up there? So something that is unclear, something where you know something and you wouldn't quite know at this point where this falls in there, or something where you disagree with this idea? Anything? No, you just believe me that this is how it is. Good. So hopefully, maybe then, so we will always come back to this scheme of model formulation, model estimation. Oh, there's an I missing. Of course, typos will be very bad now that everything is shared. So estimation, model evaluation, model formulation. So we will always come back to that, and I will always tell you when we talk about the GLM which part we are currently dealing with, it's very fundamental. And it will actually also, I can tell you that it will, to explain these steps of model formulation, model estimation, and model evaluation will be the first question on the exam that you're going to write, because it always has been the first question on the exam. Yeah? So one question, you're already safe. Good. Then let's proceed to the next thing. Sorry. It needs 2 fingers to swap to learn this. Good. The next thing then that actually relates somewhat to already model formulation is that I want to briefly cover a number of terms in terms of model classes and model estimation techniques, so that you have at least some terms already on your mind, even if we for some time in the course won't discuss them, but to give you kind of intro in some of the nomenclature. So the first thing would be talking about different model classes, because there are different model classes, and it makes sense to at least have heard some terms. So so of course this is all this is kind of zoology of what is happening in the world. So people are developing data analytical procedures every day, especially now that there's so much data available. And then one can post hoc try to make some sense of what kind of data analytical techniques or models there actually are out there in the world. And so I have some I made some binary categorizations here. So, of course, for each individual model or data analytical techniques, you then can ask yourself, so where does that fall now? And maybe there are also shades of gray where it's not really working. So a first classification of models one can do is along the lines of static versus dynamic models. So what do I mean by this? Well, this essentially already refers to a lot to the mathematical forms that models can take. So the main difference in terms of the formulation is that dynamic models are formulated in terms of differential equations, and static models are formulated in terms of equations. I say it again because I did it the other way around. So static models are formulated in terms of equations and dynamic models in terms of differential equations. So who of you has dealt with differential equations previously and solved them? Okay, so that's 3 of 22 or so. This is makes a lot of sense because differential equations are usually covered in depth in especially physics, but also math, but mainly in physics. That, of course, then is a little bit hard to understand if you don't know what differential equations are, what dynamic models are. We will discuss a form of dynamic models in the summer term, and I will provide some introduction to differential equations in this section then, namely dynamic causal models, which are fairly popular in cognitive neuroscience. The GLM that we will discuss has the interesting feature that it's actually a static model. So it's described in terms of an equation, which I've shown you previously, but is applied to some data, especially in fMRI, that is actually of what you would think of a dynamic nature, namely it changes over time. So time is a very important issue in dynamic models. That's kind of the weird thing in fMRI, so that people started to use static models to describe something that is inherently a time series. It will get a lot clearer when we talk more about really the content of stuff. But it also shows that it's a little bit, then there are gray areas in a way. So you can also interpret static models as dynamic models. But the real fundamental feature, and what I always feel a little bit strange about, is when people want to describe processes that change over time or over space, and they're really interested in this change, so in dynamics, that they then start out with non-dynamical models that are not formulated in differential equations. It's very weird, but it happens all the time. So that's static. Dynamic, our GLM will be of the static type. So that's maybe this distinction may be a little bit hard to understand. Static, dynamic, I think a little bit easier is to understand the difference between univariate and multivariate. Because as soon as you are in cognitive neuroscience and fMRI data analysis, you will hear that there are a lot of people who talk about multivariate data analysis, and then they usually, what they think of is when they talk about multivariate data analysis is terms of classification, brain reading, and deep neural networks. This is kind of the multivariate world in cognitive neuroscience and fMRI. What really the distinction is, I think, is that the question of how many data points you model at a given instant. And univariate models are those that where you model one data point, so a data point that is essentially consisting of just a scalar number, so just one number at each instance. And multivariate models are those that model and describe more than one scalar number at a given time. So, for example, the GLM, as we will see later in the course, if applied in fMRI, is actually applied in a univariate way. So for each time point that was acquired, you model the data of a single voxel. So you have one number to describe all the time. DCM, for example, although always thought about of something that allows you to study effective connectivity, whatever that should mean, is actually a multivariate data analysis technique because you describe multiple data points at each instance. So that's another distinction, univariate. So for now, we can think, okay, GLM is a univariate technique, and then there will be cool people who tell you about their classification multivariate techniques, but there's more to all of this. Another distinction that you can make, and this is also very much driven by how people in brain imaging talk, is along the lines of encoding versus decoding models. So encoding models are basically what we will talk about all the time, because it's kind of a model, it's kind of the fundamental of model-based approach. So encoding means that you formulate a model, somehow relating your experimental manipulations to some data that you will acquire. Decoding models it actually refers more to a use of models that you try to infer the experimental manipulation from the data. So really at the heart, these are not different models, although they are always called like that. So that you have encoding, decoding models. It's not very meaningful, but this binary thing exists nevertheless. So whenever you have a decoding model, you can write down the model behind that once the parameters are estimated, and then you have an encoding model. So there are no decoding models. It's like there are no, it's just a use of some models in some specific framework to do statistics that are maybe not that worked out yet. So yeah, so these terms exist, encoding and decoding models, but they are not really meaningful in my opinion. So let's just stress again. So the GLM is a univariate model, it's a static model, and we will of course treat it as an encoding model. So we will discuss how it looks like. So what else do we have? Okay, that was already the model classes. So our GLM, like I said, static, univariate, and looked at from an encoding perspective. The nice thing is that by introducing the GLM like that, you will always think that multivariate and dynamic and decoding models are much more interesting than what we are doing here. But believe me, that to start with the GLM actually helps to then also familiarize yourself with a dynamic multivariate decoding models, and also to see the parallels. So the GLM as a static univariate encoding model is really helpful to get started on model-based analysis. So questions about these differences here, or disagreements where you say, but I know this modeling data analysis technique which is both static and dynamic, or which is both encoding and decoding. Anyone? MVPA, yeah. So what's MVPA?
Multivoxel pattern analysis.
Multivoxel pattern analysis, yeah. So that, so, and how would you classify MVPA according to this?
Decoding or encoding or decoding model. It's also used in dynamic and statistic use.
Okay, so I know what you mean by that. So yeah, you're right. So people apply. So that depends on what people really mean by that. So if people apply, so if you're saying there's something like dynamic MVPA, I would actually call that dynamic causal modeling, because when people classify data vectors over time, this doesn't make for a dynamic model, because they just they are not interested. So they try to extract information over time, but they haven't built into the model a notion of dynamics in the physics sense, namely as a differential equation. So if you describe the rate of change, and this is what you're trying to describe with your model, then I would call this a dynamic model. If you are describing not the rate of change, but the state at a given time, I would not call this, and physicists wouldn't call this a dynamic model, but a static model. So this is, but it's a good point that you raised, because the people mean different things by the same words, and I try to explain what I mean by these words here. But there's a lot of, there's quite some high uncertainty about what people mean when they say dynamic, especially. Yeah. So I mean models formulated in terms of differential equations. So for those who are not familiar with the term MDPA, multivoxel pattern analysis, we will talk about this in the summer term. For the moment, you can maybe think that this is the cool analysis that you don't learn about in your class. It's not the cool analysis. Good. So then we have a little bit of time left to maybe a little bit too little time, but who knows? Let's see. These were model classes. The next thing that I want to briefly mention, I think, we just briefly mentioned that because to talk about it in depth is actually part of this course and other courses that you could take. So model estimation techniques. There are two things two terms at least that always come up in terms of model estimation techniques, namely the frequentist approach and the Bayesian approach. So frequentist and Bayesian. So these are terms. Who has heard the terms frequentist and Bayesian? Who has heard the term frequentist? Who had a course in statistics? That's everyone, but you haven't heard the term frequentist. Okay, so what you most likely learned in your statistics course was frequentist statistics. So because you all said that you learned about t-test. So this is classically known as frequentist statistics. Then there's something also called Bayesian statistics. So so you had statistics courses. Who of you in their statistics course learned about Bayesian approaches? Okay, that's not that many. So I assume most of you then did the frequentist approach. So what are these terms? Well, that's a very long story, and of course, definitely not. I will not answer with the next few minutes everything that there's to know about frequentist and Bayesian statistics. So there are kind of two or more fundamental differences. So maybe let's start from what you get. So in a frequentist approach, what you get out of a data estimation in a frequentist approach is essentially point estimates. So if this line describes all the different values that a given parameter could take after, and this is something you will also see in this course. So let this be the parameter value that is true but unknown. So this is actually what's happening in reality. So in reality, there is this parameter value, and it's symbolized by this black dot there. In a frequentist approach, what you will get is a point estimate of that, so something like this, which then says, okay, this is what I think this real parameter is. In the Bayesian approach, what you will get, among other things, is a description of your uncertainty about this parameter value once you've seen the data. So that's kind of a typical Bayesian thingy. And from this, you can, of course, also extract then point parameter estimates. Yeah? So that's frequentist, where you get point parameter estimates. Actually, the whole story about frequentist Bayesian statistics is much broader than this kind of difference between what you are trying to estimate, whether in terms of point estimates or Bayesian estimate, uncertainty estimates, because it also relates to how you think about probability. So frequentists typically think about probability in terms of large sample limits, so that you that there is a real probability out there in the world, and if you could forever observe something, then if you compute the long-term average of this thing that you observe, then you get to the probability of something. The Bayesian approach, especially the very subjective Bayesian approach, treats probabilities as descriptions of subjective uncertainty. So it's not something that is out there in the world, but something that describes your your own uncertainty. So the important thing is actually in what I just said last, namely that both approaches use probability, and this is why I actually, for what I'm doing, also in my scientific work, I hardly use the word Bayesian, because what is really happening here is that you use probability theory as something to model data. So I call everything probabilistic modeling. And then you can decide in a way what these probabilities that we are dealing with should describe. But the important thing is that the kind of the calculus or the way you manipulate probabilities, so the logic of probability theory is actually the same in frequentist and Bayesian. And then there are also things like empirical and Bayes, for example, that is really a mixed form of frequentist and Bayesian. So I really try to, and this I think is also the general, the more up-to-date view on things. So there was a big debate between frequentist and Bayesian approaches, like starting in the 50s, and then maybe with coming up again maybe a little bit when Bayesian computation was actually possible, and then later in the 90s. But that's kind of outdated. It's 2017, so although we will discuss classical statistics, frequentist statistics, and at certain points maybe also some Bayesian approaches, what this whole thing is probabilistic modeling. Yeah. Let's see. Okay. Anyone disagreeing with that? So frequentist versus Bayesian statistic. Anyone disagreeing with calling both of them probabilistic modeling? Okay, so the revolution is not that strong today. See, this is horrible. I will correct this now before I save that. This is, maybe that's the difference between doing it on the blackboard and doing it on a computer. Here I see all the typos. Probabilistic modeling. So that's actually what I'm doing. So if you ask me what my job is to pay the rent and the food for my cats, it's probabilistic modeling, which you might know under the terms of, so some people call that statistics, some people call that model-based cognitive neuroscience. I don't know, some people call it data analysis. I call it probabilistic modeling. Good. So any questions in terms of these general things right now? So So I can see definitely that it's that this is quite abstract, because we haven't put any meat to any of these terms right now. But at least you have heard the terms, and I can now go back and then refer to these terms and make clear what I mean. Another thing in terms of abstract, this whole course will be rather abstract, maybe from your perspective. Because we will use the mathematical concept. So if you at one point feel this is too abstract, then please ask for examples, because I'm interested in teaching abstract things which that cover a lot of ground, and you can have many examples and really condense a lot of things together. But of course, I can also see that if you're new to this, that if things are abstract, it's sometimes hard to tie that really to something that you also know. So please ask when you want examples, especially when we're starting with mathematical concepts. So that was the first hour, and I will stop the recording now, and we will have a break until 11:05, also 5 minutes past 11.